All right, welcome back to our video lecture series on discrete mathematics and its applications. Still in the topic of relation, part 3, properties of binary relation. This is the second video and in the first video, in the previous one, you were here. I asked you to solve this exercise. So are you done with that? If you're done, we could continue with the solutions, but if not, then please pause the video and try solving the exercises first. Okay, now let's continue with the solutions. For the first questions, you're given R1 binary relation over A or on A, where A is the set 5, 6 containing integers 5, 6, 7, and 8. So, is this a function? Well, because the underlying set or the domain is finite, then we could simply draw the graph. This is 5, 6, 7, and 8. So from 5, well, has to be 5 to 5 because 5 is greater than or equal to 5. And not going, and there is no other edge going out of 5. How about 6? From 6, it's greater than or equal to 6 itself, so you have this. And also greater than or equal to 5, so you have this. Now similarly for 7, you have this. And then you have 7 going out, outgoing arrow to 6, and there is an outgoing arrow from 7 to 5. For 8, you have a loop here because 8 is greater than or equal to 8. 8 is greater than 7, so you have this. And 8 is greater than 6, as well as 8 is greater than 5. Or if you want to write the matrix, it should be pretty straightforward. It's 5, 6, 7, 8. And this is 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, and 1, 1, 1, 1. So you see from the matrix as well as from the graph, it is obvious that R1 is not a function. Yeah, R1 is not a function. Or a simpler explanation without drawing the graph, you could simply write because both, for example, you take 8,5 and 8,6 are in R1. So you have more than one outgoing arrows from 8. So R1 is not a function. Now, how about the second relation? Here you have a relation on natural numbers, binary relation on natural numbers, and this seems to be infinite. So maybe we won't be able to draw a graph or a finite graph for that, or come up with a finite matrix representation for R2. But we could still draw, make a partial graph. So essentially you just take few examples of A and B and see whether we could see a pattern. So A comma B are pairs of natural numbers, and so on, and the domain is just natural numbers. So we could simply list the natural numbers. So let's list them like this. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, for example. So from 0 there is an arrow to 1. Why? Because, well, 0 is log 2 of 1, right? And from 1, there is an outgoing arrow to 2, right? Because of course 1 is log 2 of 2. Similarly, 2 is log 2 of 4. 3 is log 2 of 8, and so on. So you have 2 to 4, 3 to 8, and you could guess where does an outgoing arrow from 4 go? Well, it will go to 16, and so on, right? And and uh, and for each natural number, you have one outgoing arrow. Yeah, from 5 you go to 32, from 6 you go to 64, and so on. Now, does this hold for every natural number? Meaning that for every natural number you have one outgoing arrow, and more importantly, no more than one. Well, this could be easy, right? This has to be shown in general, but this is actually rather straightforward. So if a is a natural number, then uh, then uh, 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 then a then b, a natural number, or I should say, then the pair a comma b is in R2 if and only if a is equal log 2b, which is if and only if b is equal to 2 to the power of a. Now that means, uh, for each a natural number, for each natural number a, there is exactly one b natural number with a comma b in R2, namely taking b equals to the power of a. Yeah, so therefore R2 is a function. So you could also see that if you list the elements of R2, then essentially R2 is actually 0, 1, 1, 2, 2, 4, 3, 8, and so on. Yeah, so R2 is a function. Now how about R3? R3, well, this is rather difficult to draw, but essentially we want to know, or we want to find out, given a real number x, is there a y, an integer, such that x is less than or equal to y less than or equal to x plus 1. And secondly, given x, a real number x, is there more than one y integer, y, such that x less than y less than or equal to x plus 1. So we are trying to answer these questions. Yeah. So now for the first one, so you have two cases, right? Essentially, right? So the case one, if x is an integer, if x is actually an integer, yeah, then uh then x comma x is in R3, right? Because x is less than or equal to x and less than or equal to x plus 1. But also x comma x plus 1 is in R3. So so in fact we don't need the other cases, right? So if x is integer, then both x comma x is in R3 as well as x comma x plus 1 is in R3, because x is less, and this is here because x is less than or equal to x, which is less than or equal to x plus 1, and this one because x is obviously less than or equal to x plus 1, less than or equal to x plus 1. So actually, if x is an integer, we already have two outgoing arrows from x. So therefore R3 is not a function. Yeah, so R3 is not a function. However, if you change the condition here into x less than or equal to y less than x plus 1, then actually you may get a function, but this could be left as an exercise at home for you. All right, so R3 is not a function. So those examples show us the relations that could be a function and relations that are not a function. Now, the next property of binary relation concerns reflexivity and irreflexivity. So suppose you are given a binary relation over a set A. So R is a subset of A squared. Then we say that R is reflexive if and only if for every element of A, for every small a element of capital A, the pair A comma A is in R. So you have for every element of the set capital A, it is related to itself. So every element of the set is related to itself. That is, that if that is satisfied, then R is reflexive. Now, there is also a notion called irreflexivity. So R is irreflexive if and only if for every element of A, it is not related to itself, or in other words, A comma A is not in R. So R is reflexive if every element of A is related to itself, and R is irreflexive is if every element of A is not related to itself. Now notice here that irreflexive is not the same as not reflexive, because irreflexive means that an element of the set cannot be related to itself, whereas a relation is already not reflexive when just one element of the set is not related to itself. So this is the difference, right? So to be irreflexive, you must have all elements of A not related to itself. So let's have a look at some examples. Suppose you have 3 relations, not 5. This is some typos, but that's fine. R1, R2 to R3 over the set 1, 2, 3, and 4, and we want to determine whether they are reflexive or irreflexive, or probably neither. So for the first one, R1, one containing these pairs, is this reflexive or not? Well, to do that, it is simple just to simply draw them. 1, 2, 3, and 4. You see you have a relation 1, 1, 1, 2, 2, 2, and 2, 1, and then 3, 4, 4, 1, and then 4, 4. Yeah, or the matrix looks like, well, I draw it here, or just do it here. 1, 2, 3, 4, 1, 2, 3, 4. So this is 1, 1, 0, 0, 1, 1, 0, 0, and then 0, 0, 0, 1, and 1, 0, 0, 1. So if you look at this, there is an outgoing arrow from 1, 2, and 4, but not 3 to itself. So 1 is related to itself, 2 is related to itself, 4 is related to itself, but not 3. Or if you see the matrix here, these elements, this is the diagonal elements. Yeah, you see the diagonal elements has some 0 in it. So therefore, this is not reflexive. Is it irreflexive? Well, obviously also this is not irreflexive. Why? Because there is some element of the set that is related to itself. So to be irreflexive, no element can be related to itself. Yeah. So in the matrix, you could also see that it is not reflexive and also not irreflexive. Yeah. How about this one? Well, this is actually rather similar, but if we draw it this way, so 1, 2, 3, and 4, you have 1, 1, 1, 2, 1, 4, and then 2, 1, 2, 2, 3, 3, and then 4, 1, and 4, 4. So here you see from the graph, this is reflexive. Yeah, and this is not irreflexive. If you draw the matrix, then it should be should look like this. So it has to be here 1 1 0 1, and then 1 1 0 0, and then this is 0 0 1 0, and then this is 1 0 0 1, and these diagonal elements, they are all 1. Now how about the last one here? Well, you draw them 3 4 2 to 1, 3 to 1, 3 to 2, 4 to 1, 4 to 2, and 4 to 3. So there is no loop here, or there is no outgoing arrow from any of the element to itself. So therefore this is not reflexive, and this is irreflexive. Yeah, if you draw the matrix, then you could see that the 1 2 3 3 4 1 2 3 4 that the diagonal elements contain only 0. So if you put it here 0 0 0 0, and then 1 0 0 0, 1 1 0 0, and then 1 1 1 0. So the main diagonal element here looks, you see that they are all 0, so it is irreflexive. So R1 is neither reflexive nor irreflexive. R2 is reflexive but not irreflexive, whereas R3 is not reflexive and irreflexive, but it is irreflexive. So you have these 3 examples, and we could summarize the graph and matrix representations of irreflexive relations or reflexive relation. For reflexive relation, the graph representation would have a loop on all elements of A, loop on all elements, whereas the matrix would look like would be such that all main diagonal elements is 1. So all main diagonal elements is 1. Whereas irreflexive relation, it will have no loop at all on all elements, no loop on all elements, and the matrix would satisfy that all main diagonal elements are 0. Yeah, so that's the characteristics of representation, graph representation, and matrix representation of reflexive and irreflexive relations. Now the next one. So next we will do some exercise. I give you 5 relations: R1, R2, R3, R4, and R5. Given there, try to determine whether these relations are reflexive, irreflexive, or neither. Try this, and we'll come back with the solutions in the next video.